of foodborne pathogens for the foodborne pathogens. So, our motivation why we need to detect the salmonella and listeria, as we know that these foodborne pathogens are posing a serious threat to the mankind, and if they are not detected early, then it can cause the serious diseases. And according to the WHO, foodborne pathogens are affecting the one third of the population of the developed country, and this ratio may increase in the developing country. So that's why we want to develop the sensor for the detection of the salmonella and listeria. And and we plan to develop a DNA based sensor and onto the various platform, and we have compared the analysis on the various platform. So as we know, as the ma'am, as the Sunya ma'am also told us that how the conventional methods are not nowadays preferred over the biosensing method. So as we know that they are time requiring, and they are expensive and require trained personnel, and some cross reactions also occurs in the conventional method. So that's why nowadays researchers are fascinating towards the biosensing method, and it is acting as an alternative for the detection of the various pathogens and the diseases. So because it attributed to the various characteristic features, as it is portable system, as it biosensors are rapid, stabilized, inexpensive, highly specific, and provides a biocompatible environment to the biological recognition element also. So we have used the two electrodes here for the development of the various biosensors. So we have used the fluorine doped tin oxide electrode, then we shifted towards the paper electrode, and here we have used the metal dichalcogen based nanoparticles, because we want to explore the efficiency and efficacy of these nanoparticles, as the different morphology can, we have explored the different morphology of the nanoparticles also, because as we have seen our result that different morphology of the nanoparticles are also impacting the sensitivity and the selectivity of the biosensors. So that's why we have explored the different morphology. So here we have chosen these metal dichalcogens, that is the molybdenum diselenide, molybdenum disulfide, tungsten disulfide, and molybdenum diselenide. And um, uh, we have explored the nano broom morphology and the nano sheet morphology for the sensitivity, for seeing the impact of these morphology onto the stability and the of the biological recognition element. So we have how we have developed the electrochemical paper based devices in the in-house. So we have chosen the cellulose based paper. Earlier we have choose the Whatman filter paper also, but due to the porous nature of the Whatman filter paper, we have observed that the electrolyte and the analysis reagent is uh, leaching down. So we shifted towards the cellulose, that means the simple cellulose based paper, and then we have used here the conductive carbon ink. So so these carbon ink are used to develop electrodes onto the cellulose based paper. We have used the simple screen printing method, and through that screen printing method we have print these electrode onto the cellulose based paper, and then we have used the wax barrier. So here the wax barrier are used to avoid the overflowing of the electrode to the electrochemical readout. So that's why we have used the wax barrier. So afterwards we heat this is the real picture of the paper based electrochemical devices which we have prepared, which we have made in house. And here we can use we can mass produced these paper based paper based analytical devices. So we have seen so much differences, and we are we have seen that they are very easy to prepare, and we have seen that they are comparable to the glass based electrode, and cost also reduced to the half. So we will discuss the advantageous features of the paper based devices also. So here we have used these nanomaterials, that is molybdenum diselenide nanobronze, molybdenum disulfide nanosheets, and the tungsten disulfide nanostructures. So these all these nanoparticles, as I have told you, that these are the metal dichalcogens, as here only one transition metal, that is the molybdenum, and here in this case tungsten, and two di as dichalcogen, though two chalcogen uh, atoms were used. And chalcogen, as we know that these are the atoms which is present in the group 16 periodic table. So and all these nanomaterials are prepared using hydrothermal method. Here we use the we heat the precursor in an aqueous solution above the boiling point of the water, and then at high pressure we are able to synthesize the different morphology of these nanoparticles and at high pressure. However, the product which we obtained is very less as compared to the co-precipitation method, but we have observed that we are getting more crystalline nature of these nanoparticles. So in all these we have used the various precursors and reducing agent, and by changing the ambient conditions like pH, temperature, we are getting the different morphology. So here the first we have developed the paper-based genosensors. Here we have developed the paper-based DNA sensor for sensing the Salmonella specific DNA. First we have taken this electrode, and onto this circular region we immobilize our nanomaterial and the biological recognition element which we have taken here, the DNA, probe DNA. And then after immobilizing this nanoparticles and the probe DNA, then we have added the target DNA. Here we have used the methylene blue. So methylene blue is acting as a differential dye which is able to differentiate between the single stranded DNA and the double stranded DNA. So the principle behind the sensing is that the methylene blue shows an interaction with the free guanine basis of the single stranded DNA, but once it get hybridized, then methylene blue is not able to show the interaction, which immediately decrease the sensing signal. So this is the principle behind the sensing of this method. And here then we have added the different concentration of the target DNA, and we have obtained the results. So this is the characterization technique of MOST nanosheet, which confirms the formation of the nanosheet, as you can see in the SEM and TEM images. TEM images, transmission electron microscopic images. You can easily visualize the layer like structures of the MOS2. So we confirm that the nanosheets are formed, and we have done the UV spectrophotometer also, and the XRD. As you can see that there are very sharp peaks. So sharp peak indicates the polycrystalline natures, and here we have obtained the peak around in the region of 500 to 700, as we know that the MOS2 show maximum absorption in the visible region. So all these characterization studies confirms the formation of the MOST nanosheets. So these are the this is the electrochemical analysis data. So here you can see that when there is no nanoparticles, so here you can see very less current. You can see the very less current, but once the nanomaterials are immobilized onto that circular region, and immediately we see the difference, that there is a significant increase in the current signal. So this proves that the nanomaterial is showing the fast electron transfer kinetics. And after immobilization of the probe DNA, and we can see that there is a decrease in the sensing signal. So that decrease is due to the immobilization of the probe DNA, as due to the non-conducive nature of the biological recognition element. So there is a significant decrease, and afterwards immobilization of the target DNA also leads to the significant decrease, which can be seen, which is easily seen in this graph, and we have confirmed it through the DPV study also. And these are the different concentration of the target DNA, and we are seeing that upon changing the concentration of the target DNA, as the target DNA concentration is increasing, so the electrochemical sensing signal is also decreasing because of the non-conducive nature of the DNA. So then we have shifted towards the aptamer as a uh, uh, so why we shifted towards the aptamer? Because we have found that aptamer is providing the high specificity, and it is providing high affinity to the target. As we know that the aptamer are the single stranded DNA or RNA molecules which forms the molecular structures, unique molecular structure with the antigen. So it is very specific towards the antigen. Moreover, it is its cost is also very less, and it is providing high sensitivity, and it has unlimited shelf life, and it is repair, and cross reactivity and non toxicity can also be observed in case of the DNA aptamer. So we shifted towards the DNA aptamer, and here we have changed the nanoparticles also. So for that we have now shifted towards the MOSC2. Earlier we have used the MOS2, but when once we add the selenium in this in the precursor, we have observed that there is an increase in the electrical conductivity, as selenium is more showing more electrical conductivity as compared to the sulfur. So here we have also changed the morphology, that is the nano broom, and in case of the MOS2 we have used the nano sheath for the detection of the salmonella. But we have also changed the interface for seeing that what can be the more difference we can observe. Is paper electrode is lacking behind the electrical conductivity or not? So we have change the substrate also, that three bulky electrodes setup, where we add the 15 ml of the reagent, so that we have changed. And then we do the experiment, and we here we deposited MOSE2 homogeneously onto all the surface of the glass electrode. And then what we have done here we have used the amino modified aptamer, because in the paper electrode we are not concerned with the reusability, because as it is very cheap, so we are aim to dispose of. But here we are concerned with the reusability, so we have moved towards the approach of the covalent bonding. So that's why amino modified aptamer is used, and through the glutaraldehyde cross linking, we we go we they bonded with each other. And when aptamer comes in contact with the salmonella, and we can have this we can see the difference here. So this is the nano broom morphology. So these are the characterization techniques. So you can see that the micro rods are closed at one end and spread at other end. So this gives the conical nano broom like morphology of the MOSE2, and these are the various characterization techniques which further confirms the formation of the MOSE2. And the sharp peak further emphasize the crystalline nature of the MOSC2. And so this is the when we have the FTO electrode, then we can see the electro um, we can see the sensing signal. And once we immobilize the MOSC2 onto the surface, we can see that there is a significant change in the sensing signal. And when the aptamer is immobilized, then the sensing signal again decrease due to the non-conducive nature of the biomolecule. And here also we confirm the study through the DPV, and we have taken the different dilutions and of the salmonella pathogens, and we have found that there is a change in the electrochemical sensing signals when we have changed the different dilution of and different CFU of the salmonella species. So here we are aim to develop the paper-based biosensors for the detection of the Listeria. As we know that the Listeria is also posing a serious threat, and it is mainly found on the dairy product, and it causes a serious disease if it is not detected timely. So here also we have chosen DNA aptamers, and but we have changed the nanomaterials also. That is the we have changed we have used the tungsten disulfide nanomaterials. And then tungsten disulfide nanomaterials are physically adsorbed onto this circular region, and afterwards we have immobilized the aptamer. Here also we have taken the methylene blue as an differential sensing signal, because when it is when as you can see in this picture, this is a single stranded aptamer, but when there is no Listeria, then methylene blue can easily show interaction with the free guanine residue. But after when the Listeria is added, then this aptamers forms a unique molecular structure with Listeria, and now the methylene blue is not able to interact with the free guanine residues, which further decreases the sensing signal. So these are the various characterization techniques. So here the SAM image reveals the nanoflake-like structures of the WS2, and the sharp peak indicates a crystalline nature. And here we have done another characterization technique, that is the FTIR. So here we have, instead of using the CEV and DPV, we have used another technique for the analysis, that is the EIS technique. So EIS technique is here we are measuring the ohmic resistance. So as we know that the resistance is inversely proportional to the conductivity. So here you can find that the bare electrode is showing a high resistance, and once the nanomaterial is immobilized, then we have find that the current signal is resistance get immediately decreased. And once the bacteria, so here we can see that the resistance is further decreased when aptamer is immobilized, and when Listeria is added, then we have found that the resistance is further decreased. And here we have also added the different dilutions of the pathogen, and we observe that there is a increase in the resistance upon increasing the different dilution of the Listeria. And we have here in the real sample cases, we have spiked the Listeria in the various dairy product like cheese and milk, and we have found that our sensor is working in the complex matrices also. There is this insignificant difference. So this can also be used for the used as in commercial monitoring devices. uh, so here we have used the nano belts, nano brooms for the detection of the Listeria. So this is the again the there is this is the case in the different stages of the electrode, and this is the case when we have used the different dilutions of the or different CFU of the Listeria. As you can see, increasing the dilution upon increasing the CFU value, the resistance is also increasing due to the non-conducive nature of the microbe. So here it is the same CFU value, and here the bacteria is spiked in the cheese samples and the other. So this is the value which we got observed when the Listeria is spiked in the cheese, and this is the value which we observe when only the target, only the bacteria is present, when we have not, when we didn't spiked it in a cheese. So there is an insignificant difference in between the two. So in the summary, we can say that we have used the various platforms, and we have compared the various platforms for the detection of the Listeria and the Salmonella, and we have observed that the onto the FTO electrode, these are the limitations which we face, that the large sample volume, bulky electrochemical setup, and the large dimension. But by developing the paper based electrochemical devices, we have found that the low it is of low cost, and it can be mass produced also, and it is very simple, and have a low power requirement, and it requires very less reagent and the sampling volume. And we have also mm, found that the uh, detection limit is also uh, improved in case of the paper based electrochemical devices. So these are the benefits which we observed in the paper based analytical device, that they are disposable, cost effective, and they can be produced in house, and they are simply designed, and the volume required is also very less. So but we are also now developing a multiplex system. We are also working on the multiplex electrochemical devices for the detection of dengue and chikungunya at one platform, and we are also, as Sonia ma'am is working on the abused drug, we are also working on illicit drugs on the ketamine rohyphenol, and we are aim to develop a multiplex system for the detection of the various pathogen at one platform. And we are also miniaturizing the uh, electrochemical setup, which can be connected to the smartphone app. So these are our the future application. I have not added the my other work which are not which are related to the detection of other pathogens, and here in this slide I am focusing only to the foodborne pathogen. So last but not least, I want to acknowledge the Dr. Anu Mishra, who worked on these project as his PhD, her PhD is on this topic only, and Professor Roberto, as he is also the co-guide, and he works very hard in this project, and I'm really very thankful to the Professor Roberto and all the IAC member who invite me onto this platform. Thank you so much.
Thank you, Jagriti. Thanks for your very nice presentation.
Thank
Now
you.
we are. I am asking for some question about this presentation, and then there will be the general discussion about the pathogens by sensors. There are
Yes.